Hello, welcome to lesson 14.4.5. Now, if you've been paying attention, or you may have noticed already, is that as we've been going through talking about light over the last couple of chapters, there are some instances where it looks like light is a wave, and other instances where it takes a look at a particle. So, for example, as we've gone through chapter 13, we've talked about the reflection of light, right? Light bouncing off of mirrors and whatnot, and reflection is a property of waves. Waves reflect, and so does light. We've looked at refraction, right? The bending of light as it enters into a new medium. As waves enter new mediums or shallower waters, whatever, those waves refract, and so does light, as well as diffraction. That is the interference pattern we see as light goes through two slits. But so far in chapter 14, we've taken a look at a few things. First one being the photoelectric effect. Where it took individual photons of light, particles of light, with sufficient amount of energy in order to take an electron. There was no sort of building effect that you might see with waves. And the Compton effect is another one that we took a look at, where these particles of light, these photons, would actually interfere with electrons, and you see a conservation of momentum. Now, we started off chapter 14 by taking a look at this little h here, Planck's constant, and both of these are so essential to the idea of Planck's constant, which is why we started with that. So let's take a look at for our first example here. What is the momentum of green light? Well, we've seen this formula before. P is equal to h over wavelength, right? And so as we talked about with the Compton effect, so we can find the momentum here of this green light, 5 times 10 to the negative 7 meters. You'll find that this momentum is 1.3 times 10 to the negative 27 joule seconds per meter. Okay, give this next one a try and pause the video. We'll come back to you. See you soon. Okay, so what you should have found was 1.1 times 10 to the negative 27, because first thing you're going to do here is, given the frequency, you find that wavelength and then plug it into the formula. Thing is, though, is that when we get to things in the quantum, very small, things really beyond our kind of grasp of reality, things that we normally see as particles also have this wave-particle duality. And so the next example we're going to look at here is the momentum and wavelength of an electron moving at 1.5 times 10 to the 4 meters per second. So in this case here, first thing we're going to do is we're going to find that momentum. Now, we know the mass of an electron is 9.11 times 10 to the negative 31 kilograms. And we know that this is moving at 1.5 times 10 to the 4 meters per second. And so the momentum is going to be 1.37 times 10 to the negative 26 kilogram meters per second. So if we want to find the wavelength this is traveling at, we're going to, again, move to our momentum formula. But in this case here, because we're looking for the wavelength, we're going to divide it by the momentum. So we're going to take that 6.63 times 10 to the negative 34 jouleseconds again, and we're going to divide that by the momentum of 1.37 times 10 to the negative 26 kilogram meters per second. And so the wavelength of this photon, electron, winds up actually being 4.8 times 10 to the negative 8 meters. Right? Now, this is an electron, right? Little tiny particle of matter. Now, given its size, a wavelength like this would actually be fairly significant. Most of the time, we're not traveling at speeds anywhere close to this, and we are much more massive, which means our wavelength compared to our size is pretty inconsequential. You know, we're not going to diffract through doorways or anything like that because we go through. Okay, so give this next one a try. The muon particle, mass and speed are given. Find its momentum wavelength. Give this a try. Pause the video, and we'll see you soon. Okay, so this momentum of this muon particle, mass times velocity again, 6.02 times 10 to the negative 23 kilogram meters per second. And plugging that into the formula for momentum to find the wavelength, you're going to wind up with 1.1 times 10 to the negative 12. Now, this is where we get to de Broglie's wave hypothesis. Now, we've taken a look at this in terms of what's happened before, but de Broglie's hypothesis is that all matter exhibits wave properties. So that's all matter, not just, right? That's all matter exhibits wave-like properties, right? Related to its momentum. Now, after the photon theory became accepted, then the quantum, the Compton effect became accepted, and so de Broglie just took a look at this. And so we've got a couple of videos here for you to watch, taking a look at that. So again, pause the video. You're going to watch these couple of videos, and then you're going to come back to this one. I know it's a little bit awkward, but it's kind of just the way we're running things today. Some of the quantum weirdness that you saw with that electron diffraction always, I find, really freaks a little bit out in terms of the students in the class. So you're not alone if you have. Next thing we're going to just take a look at is the Heisenberg uncertainty principle, which basically says that it is impossible to know both the position and momentum of a particle with unlimited certainty. So to know the position and momentum of a particle with unlimited certainty. Now, this deals with a very fact of observation, winds up actually causing a change in momentum. So if you're trying to defend the position, you wind up losing information about momentum. Basically, the act of observing actually has an impact. And depending on which question you're asking, position or momentum, you're actually wind up changing one or the other. And so you can't know both at the same time. Now, again, this is significant when we get down to things, this small. However, if you try to, let's say, on your speeding ticket, which will say you are traveling at such and such a speed at such and such a location, the Heisenberg uncertainty principle is not really going to help you there because, well, the act of observing is going to change the position, but it's not going to be significant. You're talking about maybe a couple of millimeters, and no judge is going to throw it out just based on a couple of millimeters. or your speed, right? You got the position down, so you're not knowing the speed again, maybe a couple of millimeters per second, but if you're going 40 kilometers over the limit, they're going to give you a ticket anyway, so it's not very helpful for that. But it's the same idea, but when you get down to things this tiny, this small, right, it actually has a pretty big impact. So another video for you to watch. Pause this video, go to this one, and then let's come back to this video to finish off our lesson. Okay, hope you enjoyed that, and hopefully that makes things a little bit more clear. We're going to just got kind of a formula. This is a little bit of an ad hoc formula. It's not really a true formula. This really is here for us just to reinforce the concept of the uncertainty principle. This is not a question that you will be, an equation that you'll have to be using on, let's say, a diploma exam. However, just to kind of give you an idea of how this works, if we take a look at the unknown of the position and the unknown of the momentum, that's going to be, and we'll use squiggle lines there, approximately h over 2. So the uncertainty of the position here, we're knowing within about 2.3 nanometers, right? So 2.3 times 10 to the negative 9, change in position is approximately equal to h over 2. Or, to find out the uncertainty in the momentum, that's going to be h over 2 times 2.3 times 10 to the negative 9. So the uncertainty in the position, assuming again we're using standard units of 6.63, we're going to find that the uncertainty of the momentum is 1.4 times 10 to the negative 25 kilogram meters per second. And again, this is just kind of a formula because we know the position close to 2.3 nanometers, which means that we can know the momentum within 1.2 times 10 to the negative 25. The more exact this gets, the smaller this gets, the larger this number is going to get. The larger this number is going to get, the smaller this one's going to get, and vice versa, right? But you can't increase both of these because they're equal to some sort of constant. So try this question, pause the video, and see how you do. So now that you've given this a shot, uncertainty of position and momentum, again, approximately equal to h over 2, and you should have wound up with 8.3 times 10 to the negative 24 joule seconds per meter. Okay, thanks for watching.